This is my second Lineset temperature drop test, and what I've done here is at the connection point here, I've gone through where I've got my temperature probe going in here. I've got this whole area with a whole bunch of extra, besides the foam, I've got a whole bunch of bags and stuff that add insulation because I've trapped the air in, because I think the last test I may have had a little bit of leakage just around here, so I've purposely gone through and gone overkill and got some temporary insulation here just for the test. And I'm repeating the same test I did yesterday. I'm up here in the soffit. Okay, this is the second test of a Lineset temperature drop. It's the same as the other one, but at these connections through here, where I'm putting the temperature probe, I went ahead and completely bundled this up really well with a bunch of temporary pieces of foam and some plastic bags and stuff, so this is all bundled up a lot better than the first test. Okay, here I'm doing AC work, and there's a box turtle. What's he doing? Okay, this is the second test of a Lineset temperature drop. It's the same as the other one, but at these connections through here, where I'm putting the temperature probe, I went ahead and completely bundled this up really well with a bunch of temporary pieces of foam and some plastic bags and stuff, so this is all bundled up a lot better than the first test. I got a little bit less temperature drop. I also did it on a mild day. Average power is about, say, 489 watts. So the unit roughly is about 600 watts at 9,000 BTUs. So this is probably something around 7 or 8,000 BTUs. It's not, or even less. It's not going full bore. Started at 6 in the morning. Anyways, what I'm doing is measuring the temperature at the exit of the unit, and then also at the flare here, and then on the other side, right close to the flare. And I'm also measuring at the suction line here. And both lines are insulated with foam. Came with the unit. Small line, it's mostly liquid. One up here is mostly gas. Both have the stock. Insulation was kind of wimpy. Anyways, the conclusion is this particular test I only got a drop of about 4.2 degrees F, a little bit less than the past test. Across the small line, and the big line had a gain at temperature of 6.6 degrees. And that's based on, I took some data between 6:20 in the morning to 7:16. Conditions were about the same. Watts about the same. Superheat, pressure. Measured with the testo, temperature difference with the small probes. And then the large probes went back and forth. And then I went through and just did some averaging to see what the standard deviation. This stuff's all pretty close together, which means I got some good data. So here's the pressure in the suction line, 25.8. Pretty much constant through all this test over an hour. One standard deviation is only 0.6. So anyways, on this chart here, this is PSI-A. There's 100, 200. Between the two would be 1.414 roughly, so you got that's 141 psi minus, say, 15, 126 psi. So this line here, I can go locate that D because I've got the discharge temperature of 62. You follow it over, and then here is 60. Drop down, there's 62. And then the other tube, the large tube here by the evaporator, is 58. That's here, from C to D. This is C, and that's D. In fact, I should go through and label these. This is A, B, C, and D. So it drops along the line going to the evaporator coil because, again, the expansion valve is inside the outside unit here, and because you're absorbing heat, also you have a pressure drop. It's some of the liquid is turning into gas, so it's absorbing heat. So this is actually dropping. You really want to have no drop here. Here's the evaporator coil, which is inside the house, and then it has a rise because it's already pure gas. So all it can do is, it can't have any more phase change, so basically it's absorbing heat from the outside. So you got a drop of temperature going to the evaporator coil, because again the expansion valve is here in the outside unit. And this is not intuitive, drops and goes back up. So what I'm going to do is I'm going to insulate this, put an extra piece of Armorflex around the stock piece, try to get this drop to be less. Because what happens on here, this type of a drop is more of a problem than over here. And I really don't know where this occurred. This could be over here, the B could be over here. This is the expansion valve, drops down, and then I'm not measuring at the expansion valve because that's buried inside the unit. And then this is the exit of the small coming off the unit, outside unit. You have a flare connection, and this is the smaller line, runs 15.5 feet to here, and that's where the flare connection is. And I've got a testo probe here and here, so I measured this delta T, then I went back and measured this delta T in another 5 minutes, and I went back and measured these two and these two, and then all these are averaged together just to see how much. I purposely chose a time where the temperatures really weren't changing that much at all, which is like at dawn, so you've got the heat starting to rise but not very much. Here's the process. Goes through the expansion valve. There's A, which is the exit of the outside unit, and this is along the line set to B, and this is through the evaporator coil. C and D is where we have the superheat going on, which means it's all gone to vapor. This is the compression, and then you go through and have the condensing temperature. And this is subcool over here. This is the expansion valve. So compared to the test the other day, this was 4.2 before, and I had a bigger drop over here, the prior test. I had actually around 7.4. So test number one, I had 7.4, 8.5, and I've reduced that down to 4.2, 6.4. So by buttoning up around this connection, I've gone through and dropped this. So this first test I had can show what happens when you've got all this is insulated and then this is split open, and you kind of wrapped it with the stuff that's non-sticky, put foam, and then kind of tape it all, put some tape on it. And because I had the probe, some of it was not as well insulated. It wasn't just all metal pipes up in the out in the air. I had it several pieces of scrap of this in there, but this time I went ahead and put several pieces of foam, used some Armorflex around here that was doubled up, and then put some bags and stuff and tied it up, so this is all really well sealed. And so this is probably a little bit more reality. The 4.2 volt, 4.2 degrees drop in, say, 15 feet. So you're dropping roughly about 1 degree every, say, 4 feet. If it was 4 feet, you'd have be 16, a little bit less than a degree every 4 feet. That's what it's dropping. My goal is to get this to zero. Not necessarily to try to get the efficiency up, that's a good goal, is that this tends to sweat. It's up inside the soffit, and then you get, just like my hand here underneath the video light, so you get sweating, and then you have dew dropping inside the soffit. And that's the second test. I'm going to try to sometimes later draw a third one, maybe in a week or two, but I'm going to go ahead and put an extra piece of insulation on the suction line here. See if I can get this drop to be less. Two reasons. You want all the heat transfer to be in the evaporator to coil, and two is I want this outside temperature of this piece such that I'm not going to have so much problem with dew, because where I am, I'm right on the water, and you go ahead and get humidity to where you have dew form, and then there's water will come and rot out your house because you've got it landing on the soffits and stuff in there. It only takes just a little bit of the dew point, and actually you have 100% humidity sometimes in the morning. So dew's dropping on everything. And that's it. Again, expansion valve here is inside the outside unit. So you've got liquid high pressure, and then the two valves on the outside of the unit you connect the flares up to. I say valves, the flare connections here and here. This is all low pressure. Again, all this is low pressure. This represents a drop in temperature. This is temperature versus distance, and I'm showing it coming back. Temperature, degrees F. This is distance from the unit, 15.4 feet, and it comes back. This is actually pressure over here. Pressure, and it's also temperature. Temperature goes like this, and then where it's liquid it tends to go up this way. So you have horizontal lines here in this graph of pressure. This is enthalpy. And you have temperature and pressure related when you're underneath the dome, and also here at the point that is where you have this is all gas here. This is liquid and gas under the dome. This is the liquid region. So when it goes through the condenser here, this is all hot gas. You compress this, you got hot gas. In fact, there's a temperature curve. It's kind of hard to find. There's a 140 line, and I've got it going up to about, maybe, these are every 20 degrees, about 150. And then it cools here. Here's where you're starting to form liquid. This line here, quality, you've got, I think, half liquid and half gas. And over here you've got all liquid. So you got a mixture between here that's half liquid. You got go from a whole bunch of gas to just about all liquid. Right on here you have all liquid. And then this is what they call a subcooling, where you're cooling it below where it needs to be, and then you go through and you drop through the expansion valve here. And then, because I've drawn a little bit over this way, because the expansion valve again is buried in the unit, and I guess if I want to be more of a tooler, I'd go ahead and try to put a probe up here right by the expansion valve. I might do that in another day to see where this really is. And then you have, there's B, and again, I don't really know too much where this is. I'm dropping this to slope down because you have a pressure drop in order to have that happen like this, the temperature drop like that. And then you have to where this is all in the evaporator between B and C, and then you have superheat here. And the superheat I measured 19.6. That was pretty much constant the whole time I did this test. And that's measured with the Testo, a Testo 570. So it's got the pressure, the superheat, and then one of the probes during that part of the test is over here on the suction. To do superheat, you've got pressure point on the left side is on the suction, and also the temperature D. These two things will determine the superheat. And that's these two columns here, and it figures out the superheat. What it's doing is looking at the pressure and then it's calculating what the temperature has to be for that pressure, and then going through and figuring out how much hotter that actually it is. So the superheat here was around 19.4, 19.6 the whole time running this test. And then the data over here that's sort of constant, I just kind of average it all out of this together, and I could do that because all this stuff is less than about 1 unit. So superheat 19.6, 7 data points. If you go ahead and take the average outdoor condenser entering air, 81.6, and the return air wet bulb inside, 66.3. You take these two data points, and you just want to figure a target superheat if it had a fixed expansion valve. Now again, it doesn't. This has got a computer-generated gizmo that's doing what it can, because it's going ahead measuring a whole bunch of parameters trying to keep the superheat it wants. But I'm assuming, let's just for a second say I had a fixed orifice here. Well, using these two parameters of outdoor condenser and the return air wet bulb, and I go through the TruTech Tools chart that goes measured within about a degree. It's a real fine chart. Used 82 and 66. It gives 17.2. So it's fairly close to what it needs to be, 7.2 and 17.2 and 19.6. Again, what it does is this machine, right now during this test here, where it's only at 489 watts, the compressor is only going like in, I don't know, I'm just guessing like third mode. It's only going, listening to the inverter run or the compressor run. It's not going balls to the wall. It's going probably third or half speed or something like that. And then the outside fan isn't going that high. So it has a variable displacement in the sense that it's varying the RPM of this. So it's variable capacity. And then the expansion valve is electronically controlled. It's going through and looking at the parameters here of the temperature maybe once or twice on this coil. This is kind of a mystery band. And it's also looking at the discharge intake air over here. There's a probe. And it also measures the temperature of the discharge. It's 3 or 4 parameters it's looking at. And then it has a lookup table to figure out where it wants to put the valve, and actually has a stepper motor that's rotating this around to define the superheat it wants. And that's why going through and measuring the superheat here, let's say right now I'm on the money here. It still may not be, it still could be low in refrigerant when this guy ramps up and decides to go balls to the wall. And that's why a lot of these, they have a test mode that'll go through and run this extremely fast. So you've got max cooling to find out if, you know, when this valve is the position it wants to be, are you running out of refrigerant? And so that's why to charge these, they normally have you go through and, you know, you connect this up, you pull a vacuum, check for leaks, pressurize it a lot of times, look for leaks, and you pull a vacuum again, and then you go through and undo, back off the valves to allow the refrigerant to go through the system. Then you crank it up and do your first test run. If you want to go and have a leak and you top this off, you're not going to know where you are. And I had a couple other videos on that. And so that's what you normally do. If you had a big leak, you normally do is fix the leak, reclaim all the refrigerant, and then you go through and pump this down. Then you add back the number of ounces they say on the nameplate of the machine. And this one's got something like 44.4 or something like that ounces. It's a little dinky machine. There's the pH chart. There's the temperature drop, then rise to the evaporator coil, rise and return back. Superheat. This is the big small line, the big line. And this is kind of like the mystery made overseas. This is the smaller foam. The other one is slightly larger in diameter. They have on these two. And this is a piece of 1-inch Armorflex that I went through and cut a smaller piece. I'm either going to wrap both, use the stock insulation, put a big piece of foam over both, or I might just go through and wrap it around this. Now, you never want to have these together like this and wrap insulation like that. That's a no-no, because you're going to go through and send heat from here back into this. Ideally, you want to have no heat loss from any method, any gain here. You want this to go ahead and be flat across here. And you want all the usable evaporation to be in this coil. Because again, the way this unit is this entire blue line is the evaporator. It's kind of goofy in the sense that you call this the evaporator coil, but because the expansion valve is not here, this whole darn thing is the evaporator. And by my tests I just ran over here, by C it's already gone through in the second test. Everything's already evaporated. It's already all phase change. So you've got phase change mostly in here, but you do have some loss going along here. You've got some that's still coming out of solution. And so you've got maybe pure liquid here, then you may have 99, 98, 96, who knows, going along here, and that's why I've drawn this as not a solid line. And if you have a high superheat, what it means is the coil is going to be to where you're completely got gas occurring way down in here. And then you got a very little heat transfer. Like if this was the coil here, you're blowing air on this section, you're not going to get that much heat transfer. Ideally, you want to have this to be solid liquid to here, and you want all the phase change to occur in this thing. You don't really want it to be occurring along Lineset. So the goal is to go ahead and really insulate this even more, get some efficiency up, also prevent sweating.